Welcome back to 6802, and today we're talking about CW approximation. The narrative is that right now we know for X and Y CW complexes, a map that's a weak equivalence between X and Y is also a homotopy equivalence. Now, we know that not every space X has the homotopy type of a CW complex. So, not all X have a CW complex Z homotopy equivalent to X. So we don't necessarily have maps between X and Z that induce a homotopy equivalence. But it turns out that all spaces X do have CW approximations, which are not homotopy equivalent, but weakly equivalent to X. So what we're going to do is we'll weaken this assumption, or criterion, let's say. And that will give us a way to approximate spaces by CW complexes where we understand maps. So our idea might be, let's say outline. We have spaces, so arbitrary spaces, let's say like X to Y, and we know something about, and we have some map between them that we're interested in studying, or something like that. Then what we can do is we can produce CW replacements. So what that means is for any X, we get a CW complex Z and a map Z to X, which is a weak equivalence. Remember that weak equivalence means it's a pi star isomorphism. And so even though we might not have Whitehead's theorem for this map between X and Y, if we know that it's a pi star isomorphism, F, then we might be able to replace X and replace Y by CW complexes, and then make some conclusion about the map between the spaces. Notice, though, that there's some order to the, there's an orientation to the arrows here. So if you have F between X and Y, what you can do is replace X by this Z, which is CW, and then look at the composite to Y, and this here is a weak equivalence, which sometimes people denote just by a single tilde rather than the homotopy equivalent sign. The resulting map, if F is a pi star isomorphism, then this composite is a composite of two pi star isomorphisms. So if F is a weak equivalence, so is the new map from Z to Y, the composite. So, but if you replace Y by well, I've run out of letters, let's say W. That's also CW complex, and this is our weak equivalence. You don't necessarily know that you can lift this map that lands in W back to a map in Y, because weak equivalences don't come necessarily with inverse maps. So, on the level of spaces, right? So this means that you can get some sort of like lifting of Whitehead with this technology that we're going to build to say that, if you have a map f x to y that's a weak equivalence, and y is a CW complex, or has the homotopy type of a sub-CW complex, so y is homotopy equivalent to w, a CW complex, then the resulting map z to y, so the composite, factoring through x, where z to x is a CW replacement, this resulting map is, in fact, a homotopy equivalence. So, C to W, Z to Y is a homotopy equivalence. So let's state this as a theorem, and then we'll prove it. So, theorem, CW approximation, every topological space is weakly equivalent to a CW complex. In particular, we can phrase this as for all x, there exists a Z CW complex and a weak equivalence and we're going to orient things to map from Z to X. And I'll just make a note. If X is path connected, we can make Z have a single zero cell. So, which shouldn't be super surprising. Let's prove it. So our proof is, would you believe it, inductive. So we induct on cells, on dimensions. So what it's going to be is that we'll, at step n, we will construct something which is a pretty good equivalence to x up to degree n minus 1, it turns out. So here's how it will work, is that we will construct, so let's say z0 be just a single point for every path component of x. So another way to put that is just it's the set pi 0 of x. And I guess we can assume x has a space point and make it xx0. So now at every next step up, what we'll do is that we'll attach cells. And so at step n, attach a bunch of n cells to z n minus 1 so that 1 pi n minus 1 z n minus 1 union these new cells. Let's just call that Zn. So that pi n Zn with some chosen base point, so let's just call that little z. The induced map from gluing these cells into pi n minus 1 of x with our chosen base point is an isomorphism. And pi n, not the integers, but z, n, z to x is surjective. So you should think about this as we are simultaneously adding relations for step n minus 1 and generators for step n, and that's how it's totally going to work. And then I should say 3, but this basically goes in parentheses, is that pi k mapping from z n to z to pi k x naught is also an isomorphism for k less than, I guess, or equal to, but that's property 1, n minus 1. And so the idea here is that adding these n cells should not change homotopy groups in degree more than, in degrees lower than n minus 1. So adding n cells doesn't change pi k for k less than, strictly less than n minus 1, right? So we already know, I think we made you guys prove, or we proved in class, that adding n cells can affect your n minus 1 homotopy groups, and but it can't affect your n minus 2 or n minus 3, etc. homotopy groups. So part 3 comes along for free. So you should think about this as an induction where we're just like fixing one additional degree. And so how does this work? Essentially for part 1, the types of relations that we're adding, we're going to add a bunch of cells. So let's go like this. For part 1 of step n, we add a cell. And so what do the attaching maps for cells, these are n cells, attaching along the maps from Sn minus 1 to Z n minus 1 that are generators for the kernel of the map from pi n minus 1 of z relative to its base point, z n minus 1 relative to its base point, to pi n minus 1 of x relative to its base point. So you find what you need to kill, and you pick generators, so I should say chosen generators. So you look at this kernel, and inside of it you pick a generating set, and then you allow these to be indexed on that generating set. So if inside of here you have, let's raise it this way, some generating set E, I don't know, alpha for alpha A, generating set, then what you have done is you're picking these attaching maps E alpha for these cells, and then one of the two things that we're doing to get Zn from Zn minus 1 is we take S n minus 1. We take a whole bunch of these. We can either be wedges or disjoint unions, so let's let them be disjoint unions, because we might have several connected components over alpha and A. So these include into a bunch of DNs. Here are all your cells, alpha and A. So here are all the cells, all the N cells, E alpha that we're attaching. For these relations. And you have, we have one of these for each N cell, but we're attaching them along these maps, E alpha, big disjoint union of E alphas into Z n minus 1. And the push out, or gluing construction of these two guys. So Zn, although maybe I'll say twiddle because it's kind of like half of Zn, is going to be defined to be, actually let's just not give this guy a name. Let's just say this is Zn minus 1 union this bunch of N cells, E alpha. And maybe just for completion, let me put N's on my alphas so that we know that these are N cells that we're attaching. Okay, and so this is what attaching those cells looks like. And notice that because I have a map inductively, we have a map from Zn minus 1 to X. Now, out of the, and the induced map from this into here is 0, right? Like these guys, because these live in the kernel, we get an induced map. On the gluing construction, yeah, and so you always just want to think, can I make sense? This is just what the quotient topology is, right? Now, simultaneously, we also want to pick all of these generators. So for every, so pick a generating set. Let's say E n beta of maps which are attaching, they're going from Sn minus 1 to Z, to X n minus 1, just to X. These generate, so we have all of these, and this is indexed over beta in some big set B, which generate pi n of X relative its base point, right? And we also just want to attach these, and let's tweak this. This is S maps from Sn. These are going to be E. You know what? Let's not call these En. These aren't cells yet. Let's just call these I don't know, phi beta. We have all these maps that generate this, right? And so these are maps in the nth homotopy group, so they're maps from Sn into X. Then we add on cells which are attached just as like big wedges of spheres, so they're attached along the 0 map into Zm minus 1. So add for each of these a trivial cell, but extend the map that we produced up above. Let's give this a map, a name. Let's just call this F. Extend F to Zn minus 1, union all these alpha in A, En alpha, union all of these new cells, En beta in B, but which are all being attached trivially, so they're being attached along the 0 map to get this new map, and this is going to be Z to X. And so I want to extend this so that on these guys, on each of these, this is the map phi beta. Because each of these En cells looks like a copy of Sn. So let's go to the next page and summarize that. So what we have done is we are taking Zn minus 1. We're adding a bunch of cells for these generators, En alpha, alpha in A. And we're also adding on just a big wedge sum, would maybe be a better way to write it, of Sn's for, and these are indexed on beta in B. So these are glued along maps. So glued, let's just say interesting. So those are along maps given to us by the way we pick the cells living in Zn minus 1. And then these ones are attached trivially. And this comes with map into X. And by construction, when we added these cells, we satisfied condition 1. We made we made the map on pi n minus 1 of F into an isomorphism, because by inductively it was already surjective, and now we have made it injective by killing the kernel. And these guys here, in step 2, we have now made pi n of F surjective onto pi n of X, right? Which satisfies the problem. So what we have done is we're basically building a CW complex that has the correct pi 0, pi 1, pi 2, pi 3, etc. all the way up. And so what this might look like is if X is path connected, maybe X, looks like a torus or something, right? Then, well, the torus is a pretty nice case of this. Maybe it's harder. Maybe it's got more stuff, right? Then what you've done is you've added a bunch of loops. So at step 1, there's nothing to fix in pi 0 because it's already an isomorphism with pi 0 of X. And so we're only really doing the blue case of making it surject. So you attach a bunch of things making it surject onto pi 1. And then you move up a level, and what you do is you attach a bunch of 2 cells, some of which might, realize that, maybe if you gave these guys all names for what they're doing in A, maybe A, B is trivial, or is A, B is homotopic to C in X, and so you attach a cell along A, B, C inverse, right? And maybe you also attach one along D squared, because D squared is also trivial. So it's equal to the constant map in at x0, right? In pi 1. And then, so you added a bunch of new cells, and so you've got like this complicated twisting cell over here, and you've got the other ones going around A, B, and C, and now this looks bad. But then you also add in a bunch of new, spheres that you're adding on to this bouquet in order to surject onto X. And now this surjects onto pi 2 of X, and you've fix things so that it in fact is isomorphic on pi 1, and that's all the induction is doing, moving up. So just think about groups as generators and relations, and we are, inductively solving this. You could also, it's weird to call it an induction, it's just an inductive construction. You could also just pick a giant wedge of spheres which lands surjectively onto all of the generators for pi n for all n of X, right? And then you could mod out by everything that's in the kernel. So you could do these, we're doing them like at degree n, we're fixing two different things, but you could actually do these all separately. You could do all of part 2 first, and then do all of part 1. So, yeah, and that's the proof. So that is cellular approximation, or CW approximation. So it occurred to me maybe the reason I can extend F over these other cells is a little unclear. So let me just draw that diagram too. So when we're attaching, when we're taking Z n minus 1, which came with a map, F n minus 1 over to X, and we want to extend it to the map on Z n minus 1 union these alpha guys, E and alpha, and these Sn betas, this big wedge, right? You should think of it as like two things I'm attaching. So I have this big direct sum of Sn minus 1s and a base point. So this is the base point for the wedge, and these guys are including into this big direct disjoint union of dn's, it's over alpha, beta, wedge Sn beta. And so by gluing, we get these two maps into the bottom right corner. But then to get the map into X, I need to tell you what is the map doing on both dn and Sn in the lower corner. So let's scroll down a little bit. So let's write, I feel like it is more traditional to write X down here. So the data we have is Fn minus 1. And then we additionally know what the map is doing over here. So it's doing these attaching maps. So the maps, I think I called them En alpha, mapping from Sn minus 1 to Z n minus 1, and then via F n minus 1 to X, because these guys lived in the kernel. So it's doing that on one half, and on the other half, it's doing just the zero. It's mapping onto generators. So it's sending Sn on the beta summand. It's a big wedge sum of these characteristic maps, phi beta. So each of those is mapping Sn to X, and it's indexed over beta. And to know that you get an induced map like this, that this exists, you have to know that the diagram, the outer square commutes. And so tracing from the top left corner, on the point summand, we go down and over, right? And we get nothing. And going right and over, we get nothing. So like you can do whatever you want on those SNs, which is why we're allowed to freely adjoin these just like phi beta maps. And on the left summand, on Sn minus 1, like on the alpha summands, you go over and down and you're doing exactly this En alpha map, and then go down and over and you're doing the filling map, which recognizes the fact that it was in the kernel. So maybe that would be the better way to write this. So because this map, En alpha, is null homotopic, we get a map from Dn to X for each alpha. Let's call that N for null homotopy, and alpha, which is what we're doing on Dn. So maybe that helps explain things. Okay, we can also do approximation for pairs. So let's just call this a lemma. So if we're given a pair XA, they don't even need to be good pairs. A is just some subspace, so we just have A living in X. Then what we can do, and let's assume non-empty, so we have a base point living inside of A. Then what we can do is replace A by its CW complex. So let's call that, let's just call that A CW here, right? And we know that A lives inside of X, so we actually have a map from A CW into X. And now this composite, let's call this is I, this is ICW. This composite you can now extend using the same technique to a map which is a weak equivalence landing in X. Just inductively go up. On pi 0 it should at least be, well, A could be missing some stuff. So you just keep adding cells using the same induction as before. To construct from ACW a bigger CW complex. So this is a subcomplex, Z, where Z to X is now a CW approximation. So this is now a weak equivalence, but since A is a subcomplex and we didn't change A, or the inclusion of I into A, we're just adding on new cells and not doing anything to ACW, you have that inside of Z, ACW is equivalent to A living inside of X. So you can like do this pairwise replacement where when restricted to the pair, it's still a CW replacement. And there's nothing more complicated going on here. It's just we're doing this like huge brute force technique where we're attaching, infinitely many cells to rectify the homotopy groups. So you can do that without breaking anything. And so this induction this starting starts at like n equals 0 and go up. So if in particular a is like just the base point x0, but x has multiple connecting components, you're going to have to add additional points to z, but you don't have to change what you're doing on ACW. So now, if A already captures a lot of the low-dimensional homotopy groups, so if A into X is already, let's say, n-connected, which it occurs to me I have not yet defined, so let's do that. Sub-definition. N-connected map is a map which induces isomorphisms on pi k with k strictly less than n and surjections, and a surjection on pi n. So a good example is this map that we had Zn onto X in our proof. Was an isomorphism on degrees less than n and a surjection on degree n. So this is n-connected. So another way to rephrase the proof is we kept creating more and more connected spaces or maps covering X until eventually n was infinity, and then we had an isomorphism on homotopy groups. So the way that perspective is that what we really did was we inductively produced Z0, and this is 0 connected, and then we constructed out of Z0 Z1, and this map here was 1 connected, and then Z2, 2, and this was 2 connected. And we kept going up, and we ended up eventually with something that was infinitely connected, and infinitely connected maps are isomorphisms in all degrees, and therefore they are weak equivalences. Okay, so I was saying, though, that let's go back to black. So if A to X is already n connected, well, then in order to produce a CW replacement aside from inside of A, you could just attach cells above degree n, because you just have to fix surjectivity in degree n, which means attaching n+1 cells. Fix injectivity in degree n, which means attaching n+1 cells. So if this is already n-connected, you can produce something, okay, and there's no definition for something cellular if A isn't cellular, so let's say this and A is CW, and I guess this does not need to be an inclusion as I've written, this could just be a map, then we can do the same argument, same construction, to get Z with A living as a subcomplex where this is the map from Z to X is a weak equivalence, and this is n-connected, and Z minus A only contains cells in dimension strictly greater than n, so in degree n plus 1 and above. I have phrased both of these things as propositions. They were both just observations from making arguments, but they're good to formalize. Sometimes this is stated as if A and X are already a CW pair, but really it's just you're starting with, like, if you pick some subspace of X or a map into X which is already CW up to a certain point, you can just start your induction, which is already a n-connected replacement up to that point. You can use n, use A as Zn, and then you just keep doing the same proof, and you produce this Z by only attaching cells in degree n plus 1, n plus 2, etc. Maybe the last perspective on this is if XA is CW, is already a CW pair, and A into X is n-connected, then this argument produces a new CW pair, ZA, which is homotopy equivalent because it's a weak equivalence and everything's a CW pair, to XA. But that homotopy equivalence happens relative to the subspace A. Because we are only attaching cells in degree outside of A. So the only difference between X minus A and Z minus A, between X and Z, are Z has presumably these many, many more cells than X, and the weak equivalence that we produce gives a homotopy equivalence, and through Hurewicz theorem, and if you look back at Hurewicz theorem, we had this relative version that said, well, if you already know that you're a homotopy equivalent on a subspace, you can get the homotopy equivalence relative to that subspace. And so because we already have that A is homotopy equivalent to A, we get this for free just from Hurewicz. So let's just write that down. I'll go proof. Sorry, not Hurewicz. from Whitehead. My apologies. So the next thing I want to discuss is Postnikov towers. And I do have some space left on this page, so let's just scroll down. So Postnikov towers are another way of approximating a space. And in some sense they're dual, although they're not formally dual. So for the category theorists, I warn you, there is a lack of duality in these stories. But Postnikov towers are kind of the other way to build up this story. So, or to build something weakly equivalent to X from it by attaching cells. So on one hand, we have this space X, and we can produce inside of it Z0 with a map that's 0 connected. This goes up to Z1, up, etc., etc. This is 1 connected. And we ended up with, eventually, a Z that was weakly equivalent to X, and it was CW. Right? That's the story we have so far. What we're going to do now is instead build something bigger than x. So what we'll do is we'll build something over here, and the maps, rather than x receiving a map from our replacement z, x is going to map into our replacements. And the maps in here go the other way. So we're going to end up with a tower like this. And whereas over here, Zn only had cells in dimensions less than or equal to n, in the red side of the picture, our requirement is going to be that pi k of xn is 0 for k bigger than n. So you should think of the red picture as I'm trying to get rid of the high fuzz in the left picture. So, yeah, I don't have that much space. So think about at like a given stage over here, we had this map, it's n-connected, but if you look at the higher homotopy groups, it could be that x's, higher homotopy groups are maybe nice, maybe they become 0, are, maybe they're tame in some way. But ZNs, we know, actually are atrocious, because one of the things that we did when we stopped attaching cells is we added this big wedge of SNs. And so, let's put it this way. This has all the higher homotopy groups of spheres, and kind of more garbage going on in degree bigger than n. So I'm talking about pi strictly bigger than n over here. So maybe this deficiency of our blue approximation, we are going to attempt to rectify it in the red approximation. And now the niceness criteria, so 0 connected, 1 connectedness on the left, is going to be somewhat similar. We're going to require that the map from x to x n over here on the right, where n is allowed to be bigger than or equal to 1, not 0, over here, this has to induce an isomorphism in degrees less than or equal to n on homotopy groups. So induces pi k isomorphisms for k less than or equal to n. So it is important to note, n-connected over in the blue side, right? That means isomorphism below degree n and surjection on degree n. On the right side, when you map from x to x2, x2 has all the right 0th homotopy, 1st homotopy, and 2nd homotopy, but above that point, it has nothing, right? And so, whereas over here in the Zn approximation, what we have done is we have the right homotopy groups up to degree n minus 1. In n, we have all the right generators, and in degrees bigger than n, it is insane. There's like garbage galore that we have to come along and kill later on by attaching tons and tons and tons of cells. Now, the final nice thing on the right is, in fact, we're going to construct these by making all of these maps inclusions. So not the maps down in the tower, but we're going to build x1 and x2 and x3 by attaching cells to x. Now, the requirement on the right-hand side is X needs to already be a CW complex in order to do this. So we're going to say, let's start with something CW, right? Now we know that this blue approximation to the CW thing kind of sucks. In particular, if X is finite CW, the blue side has infinitely many cells and has them in all dimensions going up, most likely. And certainly it'll continue having cells above the point where X has no cells. On the right picture, maybe this gives us a little bit finer control. So let's construct our Postnikov towers. So how does this construction go? We're going to start, constructing. We're going to assume X is CW. I'm also going to only ever alter the base point component of X, and I'm only going to ever be attaching cells. Those are my only tools. So we are only attaching cells, perhaps inductively, to the base point component. You'll see that this proof, we only really care about the cells in and homotopy groups in the base point component. So the other components only ever show up in pi 0 and pi 1, and all the higher groups, because we're taking based homotopy, only see the base point component. So that's where we need to do work. So let's recall our desired properties for these maps. So our requirements are, I've just written them here quickly. One is that we want this inclusion from x to xn for all xn. So we have to n varies over all integers bigger than or equal to 1. We want the map in to be a pi star isomorphism for k or for star less than or equal to n, so in degrees less than or equal to n. It has to have the same homotopy groups. And xn has no higher homotopy groups in degrees above n, strictly above n. This is sometimes called either being co-connected or truncated, having the homotopy depth of some n or n minus 1 or n plus 1 truncated space. It is always worth being careful about your indexing there, and I'm not going to specify it here. And then we also want to have maps down in the tower that commute. So we have all these maps from x into these guys, and we want a map from x3 to x2 that makes the map, that commutes with the map from x. So how do we do this? What we do is we construct xn from x, and x is a great place to start because x already has all of the correct homotopy groups as x in degrees less than or equal to n. All we really want to do is kill the higher homotopy groups. So our goal is to kill pi n plus 1, n plus 2, and etc. And in order to do that, in order to eliminate elements from pi n plus 1, for instance, the lowest one, what we need to do is add n plus 2 cells. So for every element of pi n plus 1, or for a generating set, we add n plus 2 cells, eliminating them. Now, when you do this, it might be that you have picked a shitty generating set, and so there are some new elements that show up when you add in all of these cells. So a common example is like maybe you picked your generators inefficiently, so there's some element a in pi n plus 1, and you've attached, I don't know, maybe your generating set, you had both a and minus a in there. And so what you did is you attached like a cone, right, onto a, but you've also attached a cone onto minus a. And if you look at it, that means that what you have is a new element of pi n plus 2. And so when you're adding on these n plus 1 cells, it's possible that when you glue in these n plus 2 cells, some of them aren't trivial because they've been glued to something that, maybe is trivial for a different reason. This can also happen if, for instance, you attach something to A, like in this example, but maybe A already has some relations on it. So maybe like A squared is already trivial in the group. If A squared is already 0, then when you do this, path twice, A squared now has 2 reasons to be 0. It has both, if you look at whatever A squared looks like, represented for its loop, it has one cone which is recognizing the fact that A squared is null homotopic just already in the space, in X. But then also you've now attached this cell below, which is recognizing the fact that A is 0. And so, of course, also when you square that, A squared is 0 as well. And so this also gives you a new element of pi n plus 2. So, but that's okay, right? So if to kill all of the degree n plus 1 stuff, we add a bunch of n plus 2 stuff, then we just throw in those new elements to what we have to kill when we kill pi n plus 2. So that means we're going to inductively construct what you might call, let's give it a name, construct, we're trying to truncate, so let's just call it T, K, comma, N, from T, K minus 1, comma, N. And our base case is going to be T, N, comma, N is equal to X, right? And what we're going to do is we construct it by killing right, so what we want is tk, comma, n has no homotopy groups in degrees up to, from n less than, and up to degree k. Yeah, and so in this dumb base case, the equality doesn't hold, so in degrees star between these guys, right? And so what we do is, in order to make it have no, for instance, so the first case is k equals n plus 1, right, is we add n plus 2 cells. So we add k plus 1 cells to kill all the elements of pi k of t k minus 1, comma, n. And then the new thing is going to be t k n, and you repeat. So in other words, and maybe just to put this more plainly, so we add k plus 1 cells to kill pi k of x and any new garbage we've added in pi k. So let's just think about our target goals here. So what we wanted to do was to make a map from x into xn. So we did that because we've added cells, so we have an inclusion. And we want it to be a pi k isomorphism for all k less than or equal to n. If we repeat this adding cells argument to infinity, we get, we get part 3. And it's definitely a pi k isomorphism because we haven't added any cells in degree n plus 1, which is where we could potentially have killed things in degree n, and we haven't added anything in any degrees lower than that. And now the only thing really to check is part 4. So let's just write those things down. So how have we addressed all of the requirements? So 1 is x is included into xn, and xn is defined to be this limit of the t, as k goes to infinity, of the t k n's in our construction. 2 is that we've only added cells in degrees strictly bigger than or equal to n plus 2, so we can't change the homotopy groups in degrees n and below. And 3 is by construction. Let's go to another page. So for part 4, we need to look at what it means to get a map. So we have a map into xn and also into xn. Let's do xn plus 1 and into xn. And our question is, does this map exist? Oh, what we should realize is, so let's call this in plus 1. In plus 1 we get by attaching n plus 3 cells and above. And by the extension lemma, we can extend in from x to xn plus 1, provided that xn has no homotopy groups for all the cells in xn plus 1 minus x. So provided pi k of xn is 0 for all k such that xn plus 1 minus x has a k cell. But we only have k cells for k bigger than or equal to n plus 3, and that's definitely true, because in fact this is true for all k strictly bigger than n. So it is very easy to produce this map just by extension. So in some sense, what we proved with the extension lemma was that the obstruction to extending these maps over additional disks lies in homotopy groups, and yeah, we're good. Oh, I see a mistake, which is that this should be a k minus 1, because I need to know about my attaching maps. That's the degree that we got for the extension lemma. So that's k minus 1, which means k has to be bigger than n plus 1, and that is true for k bigger than n plus 3. Yeah, this is true, right? So we need it for k bigger than or equal to n plus 3, but we actually have it for k bigger than or equal to n. So we're totally fine.